Welcome back to AI Research Weekly, your deep dive into the bleeding edge of AI research. I'm Nova, and with me, as always, is Onyx.
Great to be here, Nova. This week, we've seen a fascinating convergence of advancements across generative AI and a stark, sobering look at the current limitations of autonomous agents. It feels like the field is simultaneously accelerating and hitting some very practical walls.
Absolutely. On one hand, generative models are pushing the boundaries of realism and control, particularly in audio and multimodal contexts. But then you look at agents, and the benchmarks are telling us we're still grappling with fundamental challenges in long-horizon tasks and real-world grounding. It's a tale of two AI cities, almost.
It really is. We processed 466 new papers this week, and the top signals clearly point to a focus on robustness and generalization for agents, alongside more efficient and controllable generative models. Let's start with a big one in generative audio, shall we? Voxtral TTS.
Voxtral TTS. This paper immediately caught my eye, especially with the claims against established players. Onyx, lay it out for us. What's the core contribution here?
So Voxtral TTS is making waves in multilingual voice cloning. Their key finding is a staggering 68.4% win rate over ElevenLabs Flash v2.5 in human evaluations for naturalness and expressivity. That's from as little as 3 seconds of reference audio, which is a significant practical improvement.
68.4% over Flash v2.5? That's a huge delta in subjective human evaluation. What's driving that kind of performance? Is it just throwing more compute at the problem, or is there a genuine architectural innovation?
It's definitely architectural. They've adopted a hybrid approach, combining autoregressive generation for semantic speech tokens with flow matching for acoustic tokens. This setup leverages the strengths of both, autoregressive for long-range consistency and flow matching for rich acoustic detail. What's really clever is Voxtral Codec, their novel speech tokenizer. It uses a hybrid VQ-FSQ quantization scheme, one semantic VQ token plus 36 acoustic FSQ tokens, achieving a total bitrate of just 2.14 kilo for 24 kHz mono waveforms.
That low bitrate is critical for deployment, but I'm curious about the multilingual aspect. Does this hybrid architecture truly generalize across languages, or does it show biases? And how do they handle the notorious challenges of text-to-speech without explicit text-phoneme alignment?
Good questions. Their Voxtral codec incorporates an ASR distillation loss. It aligns the post-VQ semantic embeddings to Whisper's decoder hidden states using cross-attention, which helps learn text-aligned semantic tokens without needing external aligners. This is a crucial step towards robust multilingual performance without explicit phoneme mapping for each language. It supports 9 languages currently, and the design is explicitly for low-latency streaming inference, which points directly to practical deployment.
So they're baking in that linguistic understanding at the tokenizer level through a smart distillation process. That's a big deal for reducing the engineering overhead for new languages. My only lingering thought is the subjectivity of human evaluations. While 68.4% is impressive, the space of naturalness is vast. Does it hold up under scrutiny for diverse use cases, like emotive speech or complex narrative delivery, beyond just general expressivity?
That's a valid point, and something all generative audio models grapple with. However, their evaluation setup, involving native speakers blindly rating audio quality across 60 text prompts for cloning and 77 for flagship voices, does suggest a robust methodology. It's a strong indicator of perceived quality, and the low-latency design makes it suitable for real-time agent interactions, which demand both speed and quality. This pushes the envelope for high-fidelity, efficient, and versatile voice synthesis.
Shifting gears to generative visuals, let's talk about macro. Multi-reference image generation is a tough nut to crack, especially as you increase the number of input references.
Indeed. Macro, or advancing multi-reference image generation with structured long-context data, directly tackles this problem. The core issue they identify is a fundamental data bottleneck. Existing datasets simply lack structured long-context supervision, which causes current models to degrade significantly as reference images increase.
Right. I've seen that degradation myself. You feed in more conditioning, and the model starts hallucinating or ignoring inputs. So what did they do to fix that data bottleneck?
They introduce macro data, a massive data set of 400,000 samples. The key is that it features up to 10 reference images per sample, systematically organized across 4 distinct tasks: customization, illustration, spatial reasoning, and temporal dynamics. This structured approach, with 100K samples per task and an average of 5.44 input images, directly addresses the scarcity of long context data.
That's a serious data push. 400,000 samples with up to 10 references is non-trivial to curate. Are we talking about synthetic data or carefully filtered real-world images? And how did they ensure the structured aspect without introducing a lot of human labeling cost?
They took a robust approach, Nova. They designed a pipeline that distills knowledge from advanced closed-source models and meticulously filters real-world corpora. This avoids reliance on noisy web-scraped data, ensuring logical consistency and visual fidelity. By fine-tuning state-of-the-art open-source models like Bagel on macro data, they've shown a substantial narrowing of the performance gap with proprietary models. Bagel, for instance, degraded severely beyond 3 references before this, but with macro data, it can handle more complex scenarios.
That's an important detail, distilling from closed-source models to curate an open-source dataset. It's a smart way to bootstrap quality. What about evaluation? Are existing benchmarks sufficient for this increased complexity?
No, not really. So they also propose MacroBench, a comprehensive benchmark of 4,000 samples specifically designed to standardize evaluation for multi-reference generation. It assesses generative coherence across those graded task dimensions and input scales from 1 to 10 images. This allows for a much more nuanced understanding of how models handle increasing context complexity. Ablation studies in the paper also highlight the synergistic benefits of cross-task co-training and smart strategies like token selection for managing the complexity of these long context scenarios.
So it's a complete ecosystem, a specialized dataset, a tailored benchmark, and demonstrated improvements. This is huge for moving multi-reference generation beyond mere style transfer to genuinely controllable complex image synthesis. I'm thinking about the future of creative tooling. This could enable much more intricate and consistent scene generation.
Absolutely. It sets a new baseline for what's possible when you properly address data scarcity and structured supervision in generative tasks.
All right, let's pivot from the successes in generative AI to a dose of reality in agentic AI. Slop Code Bench. The name alone suggests some pain points. Onyx, what did this benchmark reveal about our coding agents?
This paper, Slop Code Bench, benchmarking how coding agents degrade over long horizon iterative tasks, is quite a reality check. It introduces a new language-agnostic benchmark with 20 problems and 93 checkpoints, specifically designed to evaluate how coding agents degrade when they have to extend their own prior solutions under evolving specifications.
Degrade over long horizon iterative tasks. That sounds like a polite way of saying they fall apart. What's the headline finding?
The headline finding is pretty stark. Across 11 models, no agent completely solves any problem end-to-end in Slop Code Bench. The highest checkpoint solve rate observed was a mere 17.2%.
17.2%? That is incredibly low. We keep hearing about agents autonomously building entire applications, yet here they can't even solve 20 iterative coding problems. Is this a failure of planning, memory, or something more fundamental?
The paper digs into exactly that. It found that agent code quality steadily degrades over iterations. Structural erosion, which means complexity concentration, rises in 80% of trajectories, and verbosity, or redundant and duplicated code, increases in almost 90% of trajectories. When compared to 48 open-source Python repositories maintained by humans, agent-generated code was 2.2 times more verbose and markedly more eroded. This gap, critically, widens with each iteration.
So it's not just that they can't finish. The code they do produce becomes increasingly unmaintainable and poorly structured. It's like watching a junior developer on a caffeine overdose. Did they try to prompt their way out of this slop?
They did. A prompt intervention study was conducted with quality-aware prompts. While these prompts could improve initial verbosity and erosion, they utterly failed to halt the degradation of code quality, improve pass rates, or even reduce operational costs in iterative tasks. The conclusion is that current coding agents simply lack the necessary design discipline for iterative software development, meaning they can't manage architectural decisions that influence future extensibility.
This is profound. It suggests that our current pass rate-centric single-shot benchmarks are fundamentally misleading. They're failing to capture the true robustness and long-term viability of agent-produced code. We're optimizing for the wrong thing if we want truly autonomous coding agents.
Precisely. Slopcode Bench highlights a critical limitation, indicating that agents aren't just struggling with planning, but with internalizing and applying software engineering principles. This is a crucial area for future research if we want agents to move beyond toy examples.
And speaking of real-world challenges for agents, Ego2Web presents another significant hurdle: web agents that are grounded in egocentric video. Tell us about that, Onyx.
Ego2Web, a web agent benchmark grounded in egocentric videos, addresses a major gap. Current web agent benchmarks lack grounding in real-world physical surroundings. This benchmark is the first to bridge egocentric video perception, essentially what a human sees and experiences, with web agent execution.
So instead of just giving an agent a text prompt to navigate a website, you're showing it a video of a human interacting with a website in a real-world scenario, then asking it to complete a task based on that observation. That's a huge leap in complexity.
Exactly. It requires the agent to understand context from first-person visual input, then translate that into actions on a web interface. For evaluation, they developed a novel LLM as a judge automatic method, Ego2Web Judge, which achieved approximately 84% agreement with human judgment. That's a substantial improvement over prior automatic evaluation techniques for this kind of grounded task.
84% agreement is good for an LLM as a judge, which is a method we've seen gaining traction. So how did state-of-the-art agents perform on this new, more realistic benchmark? Given the Slopcode Bench results, I have a feeling it wasn't stellar.
You'd be right. Experiments with diverse state-of-the-art agents on Ego2Web showed weak performance across all task categories. It indicates substantial headroom for improvement in how agents perceive, reason about, and act within environments linked to real-world physical surroundings. The benchmark uses an automatic data generation pipeline combined with human verification to curate high-quality video task pairs across e-commerce, media retrieval, and knowledge lookup.
Weak performance sounds like a polite understatement for they largely failed. This again highlights the difference between simulated, text-based environments and truly embodied, grounded intelligence. What are the core bottlenecks here? Is it the video perception, the mapping to web actions, or the reasoning over the combined modalities?
The ablation studies in the paper highlight the critical necessity of accurate video understanding for successful task completion. It exposes limitations in current AI agents to effectively bridge the gap between complex visual input and precise action execution. It's not just about seeing, but about understanding intent and context from that egocentric view, and then translating that into a robust sequence of web interactions. It's a significant challenge for truly agentic AI in the wild.
Both Slopcode Bench and Ego2Web point to a recurring theme. Our current agents, while impressive in narrow domains, fundamentally struggle with the messiness of real-world, iterative, and grounded tasks. They lack the robustness and adaptive reasoning we'd expect from intelligent agents. It's a critical feedback loop for the entire agentic AI paradigm.
100%. It shows where the foundational research needs to focus next, building agents that don't just solve problems, but do so robustly, iteratively, and with a nuanced understanding of their environment, both digital and physical.
From agents struggling with realism, let's swing back to a generative model that's pushing realism and control in the audiovisual space. AV control. This sounds promising.
It is. AV control, efficient framework for training audiovisual controls, introduces a lightweight, extendable framework that's really smart about how it handles multimodal control. It trains each control modality as a separate LoRa on a parallel canvas, providing reference signals as additional tokens in attention layers without requiring extensive architectural changes beyond the LoRa adapters themselves.
So it's leveraging the parameter efficiency of LoRa's to decouple and modularize control signals. That's clever. How does this parallel canvas approach overcome the issues of integrating disparate modalities like depth, pose, and audio into video generation?
That's where it shines. Traditional approaches, especially extending image-based in-context methods to video, often fail for structural control because large spatial distances in concatenated layouts weaken the interaction. AV Control's parallel canvas resolves this by allowing independent yet coordinated control. For example, it supports independently trained modalities including depth, pose, edges, camera trajectory, sparse motion control, video editing, and crucially, the first modular audio-visual controls for a joint generation model.
That's a very impressive suite of controls, and training each as a separate LoRa implies significant efficiency. What are the numbers here? Does it actually save compute, or is this just architectural elegance?
It's highly compute and data efficient. Each modality requires only a small data set and converges within a few hundred to a few thousand training steps. The total training budget across 13 modalities they demonstrated was about 55,000 steps. That's less than one-third of what monolithic alternatives, like VACE, would require for a single 200,000-step run. They even show that their camera LoRa's only need 3,000 to 10,000 steps, dramatically outperforming methods like bullet time or VerseCrafter, which demand significantly more iterations and GPU hours.
That's a huge operational cost reduction, making highly controllable audio-visual generation far more accessible. And the ability to modulate reference influence globally or locally at inference time, which is something channel concatenation methods can't easily do, adds another layer of fine-grained control. It's not just efficient, it's more flexible.
Exactly. And they introduce a small to large control grid training strategy to reduce reference canvas resolution for sparse controls, like camera parameters, lowering latency without sacrificing fidelity. This comprehensive approach, modularity, efficiency, and fine-grained control, outperforms all evaluated baselines on the VACE benchmark for depth and pose-guided generation, in-painting, and out-painting, while achieving competitive results for camera and audio-visual benchmarks. It really pushes the frontier for multimodal conditional generation.
So this is a significant step towards creating complex, coherent, and controllable audiovisual content with practical resource requirements. It feels like the industry is converging on LoRa-like adapters as a core mechanism for fine-tuning and specialized control without retraining massive base models.
Indeed. The general principle of decoupling specific controls and training them efficiently on top of a powerful backbone is proving to be a winning strategy across different generative domains.
What a week, Onyx. We've seen some incredible advances in controllable and efficient generative AI with Voxtral TTS and AV Control, pushing the boundaries of realism and practical deployment. Then, on the agentic side, Slopcode Bench and Ego2Web delivered some much-needed reality checks, highlighting the persistent and fundamental challenges in long-horizon tasks and real-world grounding.
It really underscores the current state. Powerful models that generate stunning outputs are becoming more accessible, but true autonomous intelligence, especially in open-ended or embodied scenarios, remains a far more complex challenge. The gap between what looks good in a demo and what is robustly reliable in iterative real-world tasks is still significant.
My big takeaway is that the benchmarks are becoming more sophisticated and rigorous, which is essential. Slopcode Bench and Ego2Web are invaluable in pushing the research community beyond vanity metrics to address deep architectural and methodological limitations. It's forcing us to think about agent design discipline and genuine environmental grounding.
And on the generative side, the trend is clear: efficiency and modular control. LoRa-based adaptations, hybrid architectures, and novel tokenizers are making highly complex generative tasks more manageable and practical for real-world applications.
Looking ahead, I'll be watching how these new agent benchmarks drive architectural innovations that explicitly tackle iterative refinement, long-term memory, and robust grounding. We need agents that don't just solve problems once, but learn and improve their approach over time, akin to how a human engineer develops.
And I'll be keen to see the next generation of multimodal generative models build on the efficiency and control paradigms of AV control and macro. The ability to precisely steer generation with fewer parameters and richer context will unlock entirely new creative and industrial applications. It's an exciting time with clear challenges and immense potential.
That's all the time we have for this week's AI Research Weekly. Thank you for joining us.
We'll be back next week with more of the latest from the world of AI research. Until then, keep digging into those preprints.